When carrying out a statistical test about their data, it is often the case that researchers would like to show that the alternative hypothesis is true. That is, they'd like to reject the null hypothesis, which is typically the status quo or that nothing is going on, in order to show that there is something going on. Perhaps there's a difference between two groups, or maybe the mean body temperature is not the established value that people have been working with for a number of years. Or perhaps when flipping a beer cap, it's different than a coin in that it's not equally likely to come up one side or the other. If a study is well designed, there will be a high probability of making that decision. That is, rejecting the null hypothesis when, indeed, it isn't true. And such a test is said to have high power. In this video, we'll discuss more about the concept of power and the possibilities that a statistical test may result in an incorrect conclusion. When carrying out a statistical test, the first step is to define our hypotheses. For this video, we'll assume that our null hypothesis is that some parameter from the theoretical world, whether it's the probability of heads or the mean of a distribution of, say, body temperatures, is equal to some value. We'll call it our hypothesized value. And our alternative hypothesis is that the parameter is not this hypothesized value, and depending on the situation, we can use a one-sided, a greater than or less than alternative, or a not equal to, a two-sided alternative. Typically, the two-sided alternative is what we would use. We then calculate a test statistic from our data under the assumption that the null hypothesis is true. Assuming the null hypothesis is true, the p-value is the probability of observing the value of the test statistic that we got, or a value more extreme. And small p-values give evidence against the null hypothesis. Sometimes people talk about the significance level of a test. The significance level gives a cutoff for how small is small for a p-value, and it's typically denoted by alpha. Although in practice it's not always necessary to define in advance a significance level or some strict cutoff, it will help in the discussion of the concepts in this video. If we have a significance level alpha, the p-value is then the smallest level of alpha at which the data are statistically significant. And sometimes the p-value is thus called the observed level of significance. To go back to our legal analogy for a second, you can think of the significance level as the definition of reasonable doubt when we want to ensure guilt beyond a reasonable doubt. In a statistical test, the researcher typically wants to show the null hypothesis is not true, and the alternative is true. Something interesting is going on. In order to have high probability of that happening, the researcher needs high power. Since the significance level is our cutoff for how small our p-value is in order to declare a test statistically significant, it also gives us a measure of how the test performs in repeated sampling. If we did the same testing situation over and over and over again, repeatedly collecting a different sample of data and calculating a new test statistic and p-value, and then we did it again and again and again, sometimes we'd get weird or unusual data. Even if the null hypothesis is true, the data could be quite different from it. Suppose you use a significance level of 1%. Then in these repeated samples of data and repeated statistical tests, 1% of the time you'd get weird enough data that you'd get a p-value that's less than 1%, less than the significance level, and you'd reject the null hypothesis, which would be a wrong conclusion. The good news is that 99% of the time you would not reject the null hypothesis, which would be the right decision. So it sounds like a good idea to set the significance level to be very small, so that you don't mistakenly reject the null hypothesis. The problem is that if you set alpha too small, you'll never reject the null hypothesis, even if the true value is nowhere near what the null hypothesis value says it is. So we want to be able to detect a false null hypothesis. If the null hypothesis is not true, that's the conclusion we want to make. What we need is a high probability that the test will reject H0 when an actual alternative value of the parameter is true. For a fixed significance level and a particular alternative value of the parameter being true, the probability that we reject the null hypothesis is called the power of the test against that alternative. So the power is the probability of making a correct decision when the null hypothesis is false. That is, we correctly reject the null hypothesis. The higher the power of a test, the more sensitive it is in detecting a false null hypothesis. As its name implies, power is a good thing. We'll want power to be high. So, what do we need to do in order to get higher power? We'll investigate this question using the saplet. For simplicity, the saplet assumes that all distributions of data are normally distributed. The blue normal distribution at the top, labeled the null population, represents our theoretical world model under the assumption that the null hypothesis is true. Here, our hypothesized value of the mean is mu naught, which is 100, and is the center of this distribution. To calculate a numerical value for power, we need to do so for a particular value of the alternative, not just say any value greater than 100. Here, that alternative value is called mu1, and we'll start with it equal to 115. Our red normal distribution at the top is the model for this alternative worldview. It is centered at the alternative mean value of 115. Note that both the null and alternative populations have the same spread, and that's quantified by 15, the value of sigma, or standard deviation. We're interested in testing the mean, so we'll keep the standard deviation the same in the null and alternative populations. The shaded blue and red normal distributions at the bottom are our sampling distributions for the mean, x bar, or the average of our sample data. So they're the distributions of what the mean could be when it's calculated from our real-world data. As we saw previously, the sample mean or average is an unbiased estimator, so these distributions are centered at the same values as our theoretical world models. However, these sampling distributions have less spread. Recall that the standard deviation of an average is the standard deviation divided by the square root of the sample size. Here our sample size, n, is 4, square root of 4 is 2, so the standard deviation of these sampling distributions is half what it is for the theoretical world models. For this demonstration, we'll start with a significance level of alpha equal to 0.05. So this is our cutoff for a small p-value. Our alternative here is one-sided, a greater than alternative. So we're testing the null hypothesis that the mean is mu naught and the alternative that the mean is greater than mu naught. So that means that alternative values of the test statistic are values out in the right tail of the sampling distribution, assuming that the null hypothesis is true. That is, the blue sampling distribution. The red vertical dashed line shows the cutoff for values of the test statistic for which we'd get a small p-value, less than our alpha of 0.05, and then reject the null hypothesis. We won't reject for values to the left of the dashed line, but we will for any to the right, as they'd result in the small p-value. And that's indicated in the dark blue shaded region. We're looking at the blue sampling distribution corresponding to the null population or null hypothesis theoretical world model because we carry out statistical tests assuming the null hypothesis is true. But in this case, we actually know that the alternative value of 115 is the truth. So we want to reject the null hypothesis, and our power is the probability that we do so. Since the truth is that the mean is 115, to calculate this probability, we use the red sampling distribution for the alternative population, or alternative theoretical model. We still reject H0 if the test statistic is to the right of the vertical bar, and the probability that we correctly reject is shaded in pink. This is more than half the sampling distribution, and the probability works out to be 0.639. So our power, the probability we correctly reject the null hypothesis, is 0.639 for this situation. We can experiment a bit by drawing random samples of data. Clicking Sample randomly selects a sample of size 4, which is our sample size, or the value of n in this case. The sample is selected from the alternative population, since that's what the truth is here. We can see the randomly chosen sample here, and the resulting mean here. And we can see that we've correctly rejected the null hypothesis. Let's do this 9 more times. We've correctly rejected the null hypothesis 5 of the 10 times and failed to reject it incorrectly the other 5 of the 10 times. We expected to reject the null hypothesis 63.9% of the time, since that was our power. We got 50%, which is reasonably close to 63.9% for a sample of only size 10. Now let's see what happens when we change some of these values. What if the alternative value was further away from our hypothesized null value of the mean? Let's change it to 130. So our null value is wrong by a greater amount. Since we're holding everything else constant, we should be more likely to reject the null hypothesis, since the true alternative value is far from it. And indeed, the sampling distributions are quite separated now. So getting a value in the alternative sampling distribution that is greater than the value of the test statistic that would result in a p-value of 0.05 or less is extremely likely. Almost all of the area under the alternative sampling distribution. And the power is calculated to be 0.991, quite high. For comparison, now let's put the alternative back to 115, and we'll change our significance level from 0.05 to 0.1. Our criterion for rejecting H0 is now less strict. We'll reject if the p-value is less than 0.1, 10%, so we'll reject more often. As a result, the probability that we correctly reject the null hypothesis, our power, should be larger. And indeed, it is larger than our original value of 0.639. It's now 0.764. Now let's put alpha back to 0.05, and let's look at the variability. Less variability should give us more precise estimates, and that's good. So let's change sigma from 15 to 10. The distributions may appear to have the same spread, but if you look carefully at the applet, the scale is changed, reflecting the smaller value of sigma. Of course, increased precision is a good thing, and this has increased our power to 0.912. Finally, let's increase our sample size to 25. Our sampling distributions are now much more tightly clustered around the mean, reflecting the smaller amount of variability we have in our estimator of the mean. And as a result, our power goes up. This time it's so high that our program has just rounded it to 1. So to summarize, we've seen 4 different ways we can increase the power, the probability that we correctly reject the null hypothesis. The first is having a null value that's further away from the alternative. Now, in practice, this is hard to do. We wouldn't know the true value, and we want to be motivated by a null value that is scientifically interesting. So knowing this fact isn't really too useful in practice, although it is good to know that we have larger power, that is a larger probability of rejecting a null hypothesis, when we should because it's wrong by a lot. We can also increase power by increasing the significance level, alpha, so then we reject more often for larger p-values. However, there are consequences to doing this, as we'll see in a couple of minutes. Reducing the variability also gives higher power. Getting more precise measurements, perhaps by controlling for other sources of variation, is always good for helping us to make strong conclusions, and it increases power. And finally, we can get more power by increasing the sample size. When planning studies, the necessary sample size is determined by choosing a significance level and the desired power, and then determining how many observations are necessary in order to achieve that desired power for a particular difference between the null hypothesis and the alternative that is of scientific interest. Power is the probability that we make a right decision, in particular that we reject the null hypothesis when we should, because a value from the alternative hypothesis is the truth. If we think about statistical testing as making a decision, it's possible that we could make the wrong one. There are 2 types of errors we can make: incorrectly rejecting or incorrectly not rejecting the null hypothesis. These are called type 1 and type 2 errors. Not very creative names, but widely used. We make a type 1 error if we reject the null hypothesis, but it is actually true. This happens because, by chance, we happen to get data that are unlikely, so they appear to be inconsistent with the null hypothesis. If we're using a fixed significance level alpha, that is, a fixed cutoff for how small our p-value needs to be to reject the null hypothesis, The probability that we get data unusual enough to wrongly reject the null hypothesis is alpha. Suppose alpha is 5%, and we carry out 100 statistical tests, and the null hypothesis was true for all of them. We'd still expect to get some significant results, that is, get p-values that are less than 0.05, and thus we'd reject the null hypothesis, and we expect that to happen for 5 of these 100 tests. Unfortunately, for any given data and test with a statistically significant outcome, we can't tell if it's one of the 5% or not. But for any test, we have to be prepared that we could make this error. Going back to our courtroom analogy, a type 1 error, rejecting the null hypothesis when in fact it is true, is analogous to an innocent person being falsely convicted. A type 2 error happens when the null hypothesis is not true, but we fail to reject it. This is related to power, the probability we correctly reject the null hypothesis when it is not true. Indeed, the probability of a type 2 error is 1 minus the power. We denote the probability of a type 2 error by the Greek letter beta. A type 2 error typically happens because we don't have enough power, which typically happens because the sample size is too small to be able to detect the difference between the true value and what our null hypothesis says. In our courtroom analogy, failing to reject the null hypothesis means we can't say the defendant is guilty beyond a reasonable doubt. So the verdict would be not guilty, and a type 2 error would be that a criminal was freed. In practice, of course, we'd like to have low probability of both type 1 and type 2 errors. But lowering the probability of one type of error, generally speaking, increases the probability of the other type of error. Increasing the sample size can decrease the probability of both types of error. This is analogous to having more evidence in a criminal trial, leading us to be more likely to make the correct verdict. But it is often a balancing act between the two types of error, and which is more serious can depend on the context. A medical analogy can illustrate this point. Suppose we have a diagnostic medical test for determining whether a patient has a disease or not. The null hypothesis will be that the patient doesn't have the disease, and the alternative will be that the patient does have the disease. Then a type 1 error would occur if the test says that the patient has the disease, that is, rejects the null hypothesis, when in fact the patient doesn't have the disease. This would have probability alpha. A type 2 error would be not rejecting the null hypothesis, that is, the test saying the patient doesn't have the disease, when in fact he or she does, and this would have probability beta. If decreasing alpha increases beta, and vice versa, it's necessary to decide which type of error has more serious consequences, so that you can sacrifice making one type of error in order to lessen the chances of making the more serious error. But which type of error is more serious? If the disease is treatable and the patient will die without the treatment, then a type 2 error would be more serious, as an incorrectly diagnosed ill patient would miss out on the treatment. But if the treatment had its own serious side effects and the disease wasn't fatal, a type 1 error might be more serious. In medicine, all tests have associated false positive and false negative rates, with a trade-off between the two. And how to manage that trade-off needs to be determined based on the consequences for the patients. The same is true of statistical tests, where we have to consider the implications of making a wrong decision. If choosing to reject the null hypothesis, which is typically the status quo, will incur a great deal of expense, then we won't want to do that unnecessarily, so we won't want to make a type 1 error, and we'll insist on having a very small p-value, very strong evidence against the null hypothesis, before we're willing to reject it. In the next video, we'll consider some more advice about carrying out statistical tests in practice.